So I'll give you a few minutes to work on that problem. And in the meantime, I'm going to try to put this in terms of PSI. So let's see. This is for pressure. Pressure is 2008. All right, let me know when you get that value. I'd like to know that in terms of PSI and also in pounds per gallon, all right? I have the same key. Look. Okay, so any answers?
I got 4279.
4279. So this is going to be for pressure, right? And plus 3 times sigma H max, which was, what was sigma H max? 3 to 20 minus 1 to 20 minus 3500 divided, what is Q?
3.12.
Okay. And that's 4279. And what about in terms of pounds per gallon? Okay, so according then to these equations, now we know what is the minimum pressure that this wellbore can hold without having problems of shear failure around the wellbore. So this PW shear actually looks pretty close to what we computed before for PB. Is going to be somewhere over there. Very close to that. So, for example, if we were picky and say, okay, I don't want any tensile fractures, I don't want any shear fractures in my wellbore, your drilling mud window will be that. You must have your mud weight or a pressure inside the wellbore in this range. You cannot go lower, you cannot go higher, because if you do that, you will incur either on shear fractures or either on tensile fractures. Increase the pressure, tensile fractures; decrease the pressure, shear fractures. However, breakouts may not be that dramatic many times. And remember, let me bring this image back that we took a look last time at. These images are possible because you have an open hole which is stable. If it weren't unstable, you wouldn't be able to lower that imaging tool and take those images. So it is not failing, it's not moving, it is in equilibrium. At least at that time, this is stable. It has breakouts, it has tensile fractures, but still stable. So not all times these either tensile fractures or shear fractures are going to be dramatic for wellbore stability. You can have some of those as long as you don't go to some other limits where you will definitely have some wellbore stability problems. So in order to relax a little bit this condition that no shear fractures at all, we're going to do something else. We're going to allow some breakouts, some shear fracture, but we're going to compute also that what is that pressure in the wellbore that is going to allow me to determine the wellbore breakout angle. Okay? So, I'm going to explain this right now. So, before we were saying with this condition, there is a little bit of shear just at this point. However, now we're going to allow more failure around the wellbore than what we did before. And basically, the problem now consists on saying, okay, it's okay to have a little bit of failure there, and it's okay to have a little bit of failure around these 2 points. And the angle that I'm going to say I allow shear failure in, that's going to be what we call the breakout angle, WBO. Basically, in all this region, there is shear failure. And the shear failures, if we were to run a slow experiment in which we get to PW shear, and there is just failure at this point, and we decrease little by little the lateral support, we will see that shear fractures will start propagating like this and like that. And this is exactly the same. You remember that whenever we have a sample and we load it in this direction, the shear fractures, they propagate like this at a steep angle from this plane. It's the same thing over here. Those are shear fractures, they propagate like this and like that. And as we lower the pressure, this one is going to propagate like that, and like this, and like that. And very similar to you see the angle of that shear fracture. You see that it's at an angle of the interface respect to that line. It's not perpendicular to that, so this is a tensor fracture. This one here is a shear fracture. And when you progress on having this shear failure, the rock which was over here, there is now nothing which is supporting the rock. Moreover, you have the drilling mat which is circulating and probably loosening up this rock. So most of that rock is going to be removed. And now you're going to have a cavity there because that rock is not going to be there anymore and it's going to be part of drilling cuttings. And instead, in that region, now you're going to have an empty space. That empty space is what is called the breakout. And how far it goes in the intact rock is what is called the breakout angle. So here, I'm just going to draw the empty space. So over there is nothing now. And now our objective is to calculate what is the pressure in the wellbore that is going to allow me to have that breakout angle. So we still use the same equations. And let me bring this one over here. So we still use this equation, but now we say theta to be equal. What do you think that value has to be if we want just to check for shear failure at that point, according to our new definition?
19 minus half L4.5 angle.
Exactly. So you replace this into this equation, and that one plus saying that you have shear failure, these two equations, very similar to what we did before, but it's a little bit more complicated, and there is more math steps that we're not going to do here, but it's not too difficult. Sigma 1 still is going to be the hoop stress. Sigma 3 is going to be the radial stress. You're going to be able to calculate a pressure in the wellbore PWBO, which is going to be equal to PP plus sigma H max plus sigma H mean minus 2 times sigma H max minus sigma H mean, I'm running out of space, cosine of pi minus WBO, and add to that minus UCS, all of this divided by 1 plus Q. So basically, it's very similar to this one, but instead of having the 3 sigma H max minus sigma H mean, now you have sigma H max plus sigma H mean minus 2 sigma H max minus sigma H mean cosine of pi. So this is very small. This is cosine of pi minus WBO. Minus UCS, it goes over here. It will go here.
So is minus UCS also divided by 1?
Yes, correct. Yes, also divided. It's the same as in this equation over here, where also the UCS is divided by 1 plus Q. So now with this new equation, we can set a breakout angle and say, okay, I'm going to allow for a breakout angle of 60 degrees. And I think that's fine. I'm going to go with it. I'm going to have breakouts, but that's fine. And this is what I'm going to ask you. I'm going to ask you right now to, let's see, 60 degrees, 60 degrees. No, let's do it 70 because I already have the value for 70. Usually you could say, well, but can I say that the breakout angles can be 90 degrees, 120 degrees? Well, we usually no. If you use this equation, and in general, you may not want to go for breakout angles bigger than 60. Below 60, this is going to work more or less well, probably a little bit more, like we're doing in the next sample, 70. That's fine. But you don't want to go into bigger breakouts, but that's going to cause instability in the wellbore. And also, this equation is not going to work that well. So what I'm going to ask you right now is that you tell me, with this equation, and with the same parameters that you had before, what is going to be the PWBO sorry, for this angle equal to 70 degrees. Okay? So let's compute that number, and we'll see how that compares to what we have already calculated before. So notice that now we're combining the two things that we have learned before. In situ, far field stresses, and also rock strength and rock failure in order to solve these problems.
Pi is 180, right?
Pi is 180, yes. While you work on that, let me fix this equation so it fits in just in one line and not in two lines as it does right now. All right. Let me know if you get an answer. How much? No, probably that doesn't make sense.
I got 36.8.
36. Check your equations. There might be something that it is not correct. And what about that in pounds per gallon? So divide by the depth, multiply times 0.44. No, multiply times 8.3 divided by 0.44.
I got 9.81 pounds per gallon.
9.81. You have the same, Nathan?
A4.
A4?
Yeah.
Check that again, because also have 9.8. All right, so let's see now where that falls. 9.8, now it's somewhere over here. So this is PWBO for a WBO equal to 70 degrees. So now we have a much bigger range in which we can allow the mud pressure to vary. So now instead of going just up to this value of PW shear, which was very close to PV, now we can go all the way up to here without having any shear failure. So with these three simple equations, then now based on wellbore stability and based on the strength of the rock, we can determine what is required to cause shear tensor failure around the wellbore. The mud window that you will have to use for drilling still depends on some other things. For example, you may not want to go, especially if your reservoir or your rock permeability is high, below the pore pressure. Because if you go below the pore pressure, even though if your wellbore is stable, let's say you compute the PWBO somewhere over here. If you go below PP, you're going to start producing fluids, okay? And that might not be good in some location. If you get to your reservoir rock and you want to avoid formation damage, probably you want to do that because you don't want drilling mud in your high permeability sand, for example, because otherwise you're going to damage the permeability and the fluids are not going to flow very well into the wellbore. But if you're not in the reservoir rock, probably you don't want to go below the pore pressure. There is one case that you may want to do that, but we're going to talk about that later on. Something I didn't say too is that probably you remember this from drilling. If you have your wellbore pressure below pore pressure, that's called underbalanced drilling. If you go above the pore pressure, that's called overbalanced drilling. Okay, so pore pressure is something very important to keep in mind. But there is something else very important to keep in mind, that we calculated PV, but there's going to be another value that you don't want to go above that if you want to be conservative. Sometimes you could, but in general, if you want to be conservative, you don't want to go above that value. Do you have any hint of what that value might be? What did you say? You didn't say anything? Any idea? So PV, it tells you that you're going to form a small tensile fracture in the wellbore. But remember that tensile fracture sometimes is caused because around the wellbore you modify all the stresses. You create a variation of stresses which is not the far field stress. It's something different. It's just close to the wellbore, but it's different to what it is in the far field. In the far field, you're going to always have your minimum principal stress. And you may not want to go above that minimum principal stress, because if your small fracture continues propagating and it gets into the far field, it's not going to see the wellbore anymore, but just going to see the far field. And if that pressure is higher than the minimum principal stress, you're going to have a large, instead of a small tensile fracture, you're going to have a large tensile fracture. So that value is going to be S3, or the total minimum principal stress, which in our problem is 4,300 psi. Could you please compare that to pounds per gallon to see where we plotted in that line that we are drawing over there?
11.59.
Okay. So you remember that we had PV was 4320, right? So let me see if I find another color. It's red over there. So in this case, S3, it's almost around there, a little bit less than PV. So for sure, now your mud window, you may not want to go above this value. And in this case, now this is your lower bound, this is your upper bound, and therefore your mud window is going to go from there, from here, the minimum, to there. You could have a mud density that varies more or less from 10 to 11.6, and according to the calculations, you will be fine with that. There is one important assumption that we have made, and sometimes it might not hold. And you need to take that into account into the uncertainty involved in this calculation. And that assumption is that the rock has a tensile strength. We do know that, this very assumption that you have tested in the lab already many times, you cannot break it apart with your hands. It's very strong. It does have a tensile strength. But when you look at problems with large rock masses, like wellbore stability, probably you can get to locations in which, in this wellbore, you might find some pre-existing fractures. They might be tens of feet apart, but they could be there. And if you get to those, if you get to a fractured surface, what is the tensile strength of that? It's 0. And if this is equal to 0, that would mean that your PV also would be lower than this. So let's assume, for example, that we didn't have tensile strength. If we don't have tensile strength, your PV would be equal to 3520 psi. Right? Everything I did was I subtracted 800 psi from this. And 3500 psi, what would that be in terms of pounds per gallon?
Or 9.5.
9.5. And what was this one in terms of pounds per gallon? WBO was close to that, right?
9.8.
9.8. So according to these calculations, you could have here, this would be PV if you don't have any tensile strength. So according to this calculation, if you think that you are good over here, and you run into a section of the rock with fractures, your stability will be immediately compromised. So you have to be careful about that, because that's going to reduce your mud window, and it's not going to be, it's not going to keep the stability of the wellbore. Let's comment on one more very important thing over here. Let me organize this, and we'll move to that. Okay, I'm going to leave you one more experiment for you to work in at home, and I have the equation for that in my notes. I'd like to know what is, for this same problem, what is the breakout angle for PW equal to 10 pounds per gallon, okay? So you tell me that, you calculate that, and then we discuss about that in class. So what I want to discuss is now the value of PV and PW and SH mean. So let's say that you compute a value of breakdown pressure which is higher than the minimum principal stress, S3. And when you're drilling, you are drilling with a pressure that gets higher than that PV, and also that PV is higher than that S3. What do you think is going to happen in this case? If your pressure in your mud pressure is higher than S3, this is going to lead to unstable, or more than stable. Let me change this for a more accurate word. It's going to be uncontrolled fracture propagation. In this case, if you have a wellbore and you have a tiny fracture, if your wellbore pressure is higher than the calculated value of PV and is higher than the minimum principal stress, very likely, if you overcome the viscous forces, this is going to be high enough to make a huge hydraulic fracture.